class. This podcast has to do with deciding what types of bonds two elements will form. Alright? And with this, we basically talk about the idea of electronegativity. And electronegativity, if you want to jot it in your notes, is the ability of one atom to attract electrons from another atom. So again, the ability of one atom to attract electrons from another atom. Alright? And there's an electronegativity table on the backs of your periodic tables that kind of looks something kind of like this. And as we notice, fluorine has the largest electronegativity. Alright? And as you go down here towards francium, it has the smallest. So just like regular periodic trends, there's a periodic trend for electronegativity, where fluorine, the top right corner, has the highest electronegativity, and francium has the lowest. And this makes sense because electronegativity is the ability of an atom to attract electrons from another atom. So francium is a metal. It doesn't want electrons, it wants to lose electrons. So it's not going to attract electrons very strongly because it doesn't want any more electrons. Fluorine, just like all of our nonmetals, want electrons. So notice they are pretty large numbers, and our metals are fairly small numbers. And fluorine, because of its size, because it's so small, it wants an electron the most badly, or it wants it the most. So anyways, electronegativity, the ability of one atom to attract electrons from another atom. Alright, and there's basically three types of bonds, and think of it just as on a kind of sliding scale. At one end, we have what's called covalent bonds. And at the other end, we have what's called ionic bonds. In the last semester, we kind of had a rule of thumb that said ionic bonds are anytime we have a metal and a nonmetal, and covalent bonds is anytime we have two nonmetals. So kind of, again, think of this as kind of a continuum. And at this end, the covalent end, electrons are shared evenly. So again, we have two elements that are in a compound, and they are sharing each other's electrons evenly. Ionic compounds, electrons are, I'm not sure I want to word this. Typically I would say electrons are stolen. Alright, so one element steals the other one's electrons. Electrons are stolen. So they're not shared at all. But really, in all actuality, they're shared, but very, 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 very small amounts. So really, one atom has the electrons most of the time, and the other atom has lost its electrons to the one that has stolen it. Alright? And then what we have here kind of, I don't know, we'll put it this way, is we have polar covalent compounds. So they are shared, they're just shared unevenly. Which again is kind of like this one, alright? But this is really, really, really uneven sharing. And polar is, we're going to say shared unevenly. So one atom has it most of the time. And over here, one atom has it all the time, the other one really doesn't have it, okay? And anyways, we can predict what types of bonds something's going to have by how different the two atoms' electronegativities are. So on this table, we're going to just assign it some values. And from here, we are going to say, let's see, 0 to 0.3. And then from 0.3, we're going to say to about 1.7. And then over here we're going to have 4.0, which we never really reach, but we're going to go with that. So covalent bonds have electronegativity differences between 0 and 0.3. Polar covalent have electronegativity differences between 0.3 and 1.7. And then between 1.7 and 4, we have ionic bonds. Alright? So the way this works is, if we had a compound that was made of calcium and bromine, what we're going to do is we're going to come to our electronegativity table and simply find calcium, and it has an electronegativity of 1.0, and the difference between that and bromine is 2.8. And kind of think of it in terms of absolute value. So when we take this difference, we're going to find it's 1.8. So this type of compound we could predict to have ionic bonding. All right, is it the strongest ionic bonding? No, because it's not close to 4, but it's certainly greater than 1.7. So we might say weak ionic bonding. It is ionic bonding, but it's kind of towards the polar covalent bonding. All right, if we have something, let's say a bond between, I don't know, nitrogen and oxygen. So if I have nitrogen, it has an electronegativity of 3.0. These numbers have no units. Oxygen has 3.5. So its difference is 0.5. So this is going to fall somewhere up here in the polar covalent compound. So they share electrons, but what's going to be true is because oxygen has a larger electronegativity, it shares the electrons most of the time. All right? And then our last example might be something like, let's see, we'll just do a fairly obvious one. We'll talk about a diatomic element. So if we do fluorine, so fluorine always bonds with itself as an element. So fluorine is 4, and if we subtract 4, we get a value of 0. So where does this fall? This falls right here in the covalent, or sometimes it's called nonpolar covalent, but if it's covalent, it's assumed to be nonpolar. So covalent, nonpolar, covalent, same thing, but we will say polar covalent specifically if it's polar. So again, difference is 0, so it falls in the nonpolar covalent category. The last thing that we want to talk about is for this one right here. So for polar bonds, we can point where we can use an arrow. So if I were to write N and O next to each other, so N and a bond with O, we draw what's called a dipole. And a dipole is simply the direction that the electrons are flowing. And it's kind of an arrow. So we would draw an arrow that looks like this, and with an arrow pointing where the electrons are going. And at the end of this arrow, we put a little plus sign, or just a little cross. And this looks like a plus sign. So nitrogen is partially positive, where our oxygen is partially negative. So it's a pole, kind of like a magnet, has a positive and negative end. A dipole is just an arrow that shows us where the electrons are most likely to be, and it always points to the element with the highest electronegativity.